Yeah, of course. Today, I think Professor Nosé is an expert in geomagnetic field observations and also observatories. And a lot of activity is governed by the international association called IAGA. And IAGA also has a parent organization called IUGG that is going to hold its next assembly next year in Berlin, I believe. So that is where a lot of this activity for ground magnetometers is going to be discussed at the IUGG part of I'm sorry, the IAGA part of the IUGG. So so we'll just some background for the people who are joining. But I'm sure that Professor Nosé knows a lot more than I do. Yeah, perhaps we could start with so Eden, if you want to start with this smart talk today.
Okay, so thank you everybody for coming. Today, Professor Masahito Nosé is going to give a talk on geomagnetic field observations around the globe. And first, Professor Chi is going to talk about our SMART project.
Okay. I'd like to welcome everyone to join today's SMART talk. And for all the participants in this special event, we would like to say that SMART, we'd like to introduce SMART, that is a ground-based magnetometer network project sponsored by the National Science Foundation and headquartered at UCLA. UCLA has been building ground-based magnetometers for making space weather observations since 1990s. When I was a student at that time. Over the years, the UCLA team has established multiple domestic and international partners for making magnetometer measurements around the globe. UCLA students have always been a part of these ground-based magnetometer projects, but for many years their roles were mainly to assist the assembly of magnetic sensors in the lab. The situation changed shortly after the COVID pandemic that began in 2020, as you know, when the lockdowns and restrictions made a serious impact on the educational opportunities for the next generation scientists and engineers. And the SMART project responded to the national call for supporting our students during this challenging time. And we drastically increased the number of students on the project. We're very fortunate to have attracted many highly motivated UCLA students in this #1 public university in the United States. Their talent and energy have allowed us to widen the scope of their participation, and students have become the major forces in all elements of the SMART project, such as in hardware, software, data analysis, education, and public outreach and management. This fundamental change in the project structure has motivated us to create this SMART Talks series. And SMART Talks are TED Talk-like presentations, and many of you probably know about TED Talks. And these SMART Talks are given by external experts in space science and technology. SMART Talks are what inspire these experts to do what they are doing in their careers. SMART Talks are about space science and technology in action. And we invite these experts to interact with not only the SMART team, but also with members of the UCLA community. And we are grateful that the newly founded UCLA Space Institute for spreading the word of our SMART Talks. The distinguished speaker today, Professor Masahito Nosé, is a leader in geomagnetic field and geospace observations. And he's a scientist whom I admire greatly. His research and efforts have inspired me personally, and I'm sure that his smart talk today will be a source of inspirations for many of us too. I'll give the microphone to Eden, who is our smart project manager, for the introduction of our speaker. Eden.
Okay, yeah, I'll give a little introduction. Dr. Nosé is an associate professor at the Institute for Space Earth Environmental Research at Nagoya University. He earned his PhD in geophysics from Kyoto University, Japan in March 1998. And he started his career as a postdoctoral fellow at Johns Hopkins University Applied Physics Laboratory from 1998 to 2001, and then held a position as an assistant professor at the Data Analysis Center for Geomagnetism and Space Magnetism at Kyoto University in 2001, and is now an associate professor at Nagoya University from 2019. And his research interests include magnetic field variations and ion composition change in the inner magnetosphere, ground and satellite observations of the geomagnetic field, and development of a new type of magnetometer. He is also now in charge and is the vice editor-in-chief of Earth, Planets, and Space Journal, and chair of Division 5 of the International Association of Geomagnetism and Aeronomy. So, Professor Nosé, I'll turn it over to you.
Thank you for the nice introduction of myself. So let me share my screen. I hope you can see the full screen.
Yeah, we can see it.
Okay. It is my great pleasure to have this great opportunity to present my recent work in that smart talk. Today I'm going to talk about geomagnetic field observations. And here is the contents of my talk today. At first, as introduced, I'm in charge of the chair of Division 5 of IAGA. And this division treats many problems, many issues about the geomagnetic field. One is a model and observation and its data. And each of these topics are related to the working groups, as indicated here. So I briefly introduce these model, observatories, and data, and introduce these working group, three working groups. And in the latter of my talk, I briefly introduce my recent research topics of development of low-cost magnetometer and dense network using that low-cost magnetometer as a research. So let me start with the first topics. So here is the view of the Earth using the Google Earth. If you ride on a rocket on the satellite and go to the space, you may see this kind of the view. So you may think there's nothing around the Earth, in the space around the Earth, but it is not true, as you may know. There is a tenuous ionized gas that is called plasma, that consists of the positively charged particles and negatively charged particles, that is ions and electrons. And of course, they are not visible. You cannot see the plasma. And there is another thing you cannot see, that is the magnetic field. But if you have the ability to see the geomagnetic field, you may see this kind of the view. And this is the magnetic field that starts from the southern hemisphere and go through the space and the equator, and then go into the northern hemispheres. And this is the magnetic field of the Earth called geomagnetic field. And this figure is drawn by myself using my computers I calculated the location of the geomagnetic field, and these data are integrated into Google Earth and make this kind of figure. So which means the geomagnetic field can be expressed by the model, mathematical model, I mean. And the mathematical model of the geomagnetic field is called International Geomagnetic Reference Field. The short name is IGRF. And this is the same figure as shown in the previous slide. And you may see this magnetic field have the shape like a bar magnet, that is a dipole. But if you look into closely or in detail, you may notice the geomagnetic field shape is not completely different, is different from the bar magnetic field. That is the magnetic field of the Earth is expressed by the combination of many multipoles. So one is a dipole, of course, that is like a bar magnet. But in addition to the dipole, we need more complicated shape multipoles. Next one is a quadrupole, and more another one is octapole, and more. The next one is a hexadecapole, but I cannot draw this hexadecapole. But anyway, these combination of multipoles makes the Earth's magnetic field. So the problem is how much we add these dipole, quadrupole, or octapole, or more complicated poles to express the geomagnetic field. That is a weighting factor. This weighting factor is defined for a year, every 5 years. And this table shows the weighting factor for 2020 geomagnetic field. The top 3 lines is the weighting factor for dipole here. Next 5 lines express the magnitude of the weighting factor for quadrupole, and next one is octapole. And you may notice the magnitude of the weighting factor for dipole is much larger than other poles. So this is about 30,000, but other one is less than 2,000 or something like that. So which means the Earth's magnetic field is predominantly expressed by the dipole. So, but you may note, you should remember, it is not complete dipole. We need more complicated multipoles to express the geomagnetic field. So who created this IGRF model? The answer is the International Association of Geomagnetism and Aeronomy, that is IAGA. And IAGA has the 6 divisions from division 1 through division 6. And each division has their own field. For example, division 3 is discussing about magnetospheric phenomena, and division 4 is for the solar wind and interplanetary field. And division 5, which is I'm a charge of in division 5, discuss the issues of geomagnetic observations, surveys, and analysis. And this division 5 have 3 working groups. And one of them called working group VMOD. MOD is coming from the model. That working group define the IGRF weighting factors. For the latest model, 15 international teams proposed the candidate models individually. And these submitted 15 candidate models are evaluated within this working group VMOD. And there was a vote which candidate model should be used to make the IGRA. And how this model is created by the take an average or take a median or something like that. Anyway, there's a vote, and then final IGRF model is determined. And this process is repeated every 5 years. So having this IGRF model, you have a lot of information about geomagnetic field. And this figure shows the intensity map of the geomagnetic field. And from this figure, you can see the weakest geomagnetic field can be found in this Atlantic Sea or in the South America region. And the minimum value is about 23,000 nanotesla. And the strongest one is located between the Australia and Antarctic continent, and its value is about 67,000 nanotesla. In the California, where you are, is about 45,000 nanotesla, maybe here, and that is a little bit smaller than the Japan, where I am. Its strength is about 47,000 nanotesla. And nanotesla is the unit to express the geomagnetic field. And here is a refrigerator magnet. The typical magnitude of the refrigerator magnet is 1 million nanotesla. So if you compare this value with the Earth, the intensity of the magnetic field, you may notice the intensity of the geomagnetic field is much weaker than the regular magnet, which we can find in the daily life. Another interesting information from the IGRF is the direction of the magnetic field. This map shows the declination, which is defined as an angle between the true north and local geomagnetic field direction, which means the pointing direction of the compass needles. The positive declination means the magnetic field is inclined to the eastward from the true north. So looking into this figure, you see in California, the declination is about 10 degrees, which means when you use your compass in your university, direction of the compass needle is deviated from the true north by about 10 degrees eastward. But when you travel to the New York in the east coast, you may notice the direction when the declination is about minus 10 degrees. So the direction is completely different from your place to the east coast. When you travel to Japan, you may notice about between the -5 to -10. So when you use the compass in Japan, you should remember the direction of the compass is westward, not from your location. And another interesting thing, if you go to the New Zealand here, the declination is 25 degrees. So it's a very big value, very big deviation from the true north. So you should be aware if you use the compass needle in New Zealand, it is deviated from the 25 degrees from the true north. This figure shows the intensity or dipole moment of the geomagnetic field calculated from the IGRF model. As I mentioned, IGRF model is updated every 5 years. So we can see the temporal variation of the dipole moment of the geomagnetic field. In 19,000, the strength of the magnetic moment is 8.3 to 10 to 22 ampere square meters, but it continuously decreasing over 120 years. And now we have 7.7 to 10 to 22, which is 70% smaller than the about 120 years ago. So after this, we don't have no information how this magnetic field is increasing or decreasing. But anyway, during this 120 years, the geomagnetic field strength is decreasing. Okay, I introduced the IGRF model, but to create the IGRF model, I mean, to determine the weighting factors, we need the data of the geomagnetic field. So who observes the geomagnetic field? The answer is mostly by the governmental agencies. In your country, USGS, it's a United States Geological Survey, make a continuous observation of the geomagnetic field over the United States. And in case of Japan, Japan Meteorological Agency continue the observation. And also university or institute also doing the observation of the geomagnetic field. In addition to that, IAGA Division 5 Working Group, VOs, here is also supporting the geomagnetic field observations all over the world. This working group, VOs, support the training the observers in many countries and sometimes provide modern instruments because some economical worse countries have no modern instruments. So they provide, this working group sometimes provide modern instruments to such countries. And this is a picture of the geomagnetic observation in the US. Mostly that is by the United States Geological Survey, USGS. They have the 14 geomagnetic observatories in the US countries, and they are using observatory sensor packages, which have the proton precession magnetometer to measure the absolute value of the geomagnetic field, and flux rate magnetometer to measure the variation of the magnetic field, and diaphragms. This is used to determine the precise direction of the declination and inclination of the geomagnetic field. Using these sensor packages are installed in these 14 observatories. And this picture is taken their USGS homepages. This is the observatory in the Tucson, and this is in the Boulder, and this is in the Fredericksburg. This is in the East Coast, and even in the Dead Horse, that is a very snowy area. So each shed, you can see some small shed. These instruments are installed and to make a measurement of the geomagnetic field. And you may notice these observatories is located in very spacious or outskirts areas because geomagnetic fields have much interference from the artificial buildings or trains or cars. So these observatories should be located from the suburban area. The situation is the same in Japan. Here is a picture from the Japanese observatories managed by the Japan Meteorological Agencies. This is the Kakioka world-famous observatories here, and this is the Memambes in Hokkaido area, and in the Kanoya observatories. So you may notice the situation is very similar to the USGS case. So can you imagine how many observatories are made, including the old dates? This is a map of the geomagnetic observatories since 1882. So there have been more than 500 geomagnetic observatories over the world. And of course, most of them are closed, but even in recent time, more than 100 years, some observatories continue their observations. And to my knowledge, probably 150 observatories are still operating. So the geomagnetic field measurement is made all over the world, even in the small island in the Pacific area or the Atlantic seas, or even in the very severe weather condition in the Antarctic area, Antarctic continent. And these data are used to determine the ideal model, but the data are very useful for the space weather. So people or the researcher want to use the geomagnetic field data obtained by these observatories. So who disseminate this geomagnetic field data? So individual observers, that are governmental agencies, universities, or institutes who are doing geomagnetic observatories are providing their data to the public. But another way is they are also providing their data to the data centers. And data center also distribute the data, the set of the data to the users. And in addition to that, IAGA Division 5 working group GUIDAT also helps in this disseminations. This working GUIDAT define the dissemination data format. And the standard is the IAGA 2002 format. So if you know this IAGA 2002 format and you have the program, you can use the geomagnetic field data in any observatories. So this is a very standard format. And it also endorses geomagnetic indices from the geomagnetic observational data. And here is the geomagnetic field variation on November 7th to 8th, just yesterday and the day before yesterday, provided by USGS. So everyone can see this geomagnetic field data or download by the IAGA 2002 format. So you can use these data. This is from the Barrow Station in the Alaska, and this is Sitoka, and this is the Boulder, and in Honolulu. And you may notice here some disturbances in the geomagnetic field. In high latitude, the disturbance is very sudden or very jaggy disturbances. But in low latitude, the variation is very smoother than the high latitude geomagnetic variations. And variation is a little bit different between the high latitude and low latitude. And at high latitude, these disturbances is basically created by the auroral electrojet current. If the aurora appears, the very strong current is flowing in the aurora. And this westward current will create the decrease of the geomagnetic field under the electrojet current. And this aurora appeared suddenly, so that creates the sudden decrease of the geomagnetic field. And sometimes it changes very rapidly. That is the reason we can see the very jaggy disturbances at high latitude. But in low latitude, this smooth change is thought to be created by the ring current flowing in the space. Because of the westward flowing ring current, that will create the negative variation of the geomagnetic field, which is reflected by this decrease of the geomagnetic field. So using these geomagnetic field disturbances, you have the information, you may have the information, the space environment, electromagnetic environment. So to know the situation of the space, geomagnetic indices are calculated. That is a very similar idea for the economic indices, like Dow Jones Index. Dow Jones Index is to express the market situation, but we don't have. It is very time-consuming work to check each of the companies' stock values. So some people make average to express the economic situation and distribute the Dow Jones Index. That is similar to the geomagnetic indices. To see the auroral electrojet, some observatories are used to calculate AE index. To see the ring current situation, some geomagnetic data are used to calculate the GST index. The global disturbances for KP over AM indices, solar wind electric field is expressed by PCM or PCS indices. And if you want to see very long-term geomagnetic disturbances, you can refer to the AA index. So these geomagnetic indices are created and open to the public from this page, and you can make this kind of a plot. Okay, that's it for the Division 5 IAGA content. And in the rest of the time, I will briefly introduce my recent topics about low-cost magnetometer. Fluxed magnetometer is very popular and widely used in the space physics, but the problem is it is very expensive. So these three pictures shows the different types of the fluxed magnetometer made by the Denmark, and this is by the Japanese company, and this is the UK companies. So the appearance is different, but these are the instruments to measure the geomagnetic field variation, very weak geomagnetic field variations for the fluxed magnetometer, and it cost is about 20 to 30,000 or even higher. So in comparison to this fluxed magnetometer, we try to develop low-cost magnetometer using the magnetic impedance sensor. This is a magnetic impedance sensor, and here is a wire to measure the geomagnetic field strength. And also we created the electric board, including the voltage regulators, and data is recorded in the Raspberry Pi 4. And ADC is also used. So using this instrument, we created magnetic impedance sensor magnetometer around $3,000. So it is about 1/10 value of the fluxed magnetometer. So this is a comparison between the fluxed magnetometer data and magnetic impedance magnetometer data at Mineyama, the Japanese observatories. And this is a 1 hour plot for different time. And thick line or bright color is the data from a magnetic impedance magnetometer. This pale color is data from the fluxed magnetometer. And you can see both MIM and FGM recorded very small magnetic field variations. And in this case also, MIM recorded the geomagnetic field variation similar to the sort of the fluxed magnetometer. So MIM magnetic impedance magnetometer have almost similar ability to measure the geomagnetic field as a fluxed magnetometer. But it is a very low cost, so we can afford multiple magnetometers. And with these multiple magnetometers, we can construct a dense network of the magnetometer. This is a plan I'm now thinking. We have already fluxed magnetometer that is managed by the Japanese governmental agencies at Mizusawa, Haramachi, Kakioka, and Kanozan. These 4 fluxed magnetometer are installed by the government. And we installed MIM magnetometer between this Mizusawa and Haramachi here. And we also have a plan to extend to this magnetometer network to northward. And next week, I will go to this area and install MIM magnetometer at Shirakami and Mutsu. And hopefully we want to install the other MIM magnetometer between other locations expressed by these blue circles. And we want to construct this kind of a dense network in longitudinally. So using this dense network magnetometer data, we can estimate the mass density in the space very in detail. In case this is a case study for the using 4 observatories and 12 observatories. If we have only 4 observatories, the mass density estimation is made only these sparse areas. There is only small gaps. But using the 12 observatories, we can have a 2-dimensional complete map of the mass densities. And this network is aligned to the distributed array of small instrument DAISY that is proposed in the US. And maybe your supervisor, Peter Chi, may have a much knowledge than I, because this is a United States program. And this is the cover page of the workshop report published in 2006. And right figure shows the solicitation of the proposal for DAISY. So the DAISY is the next step for the ground observation in space physics. So I want to work closely with this DAISY program from Japan. Okay, that's it for my talk. Thank you for your listening.
Thank you so much for your talk. That was really interesting. Now we'll have some time for a question and answer. So does anyone in the audience have some questions?
Is there a similar movement for a similar network of observatories like in California, I guess?
I believe so. Yes, maybe your supervisor, Peter Chi, may know much about that, but yes, I believe so. In the United States, there is some project to deploy the dense network in the North America continent. Is that right? I'm not sure it's in California or what in other longitudinal, meridional plane, but maybe it's there.
Yeah. Well, I can give some feedback later on, but as we have other students raising hands, so let's go to them.
Okay, yeah.
Do we know why the Earth's magnetic field strength is decreasing?
Strengths? Is
the
this
next
slide
slide.
you are talking? Next.
The gradual decrease from 1900s.
Oh, okay, sorry.
Yeah,
Yes,
this one. Do we know why it's happening?
Excuse me, sorry, I couldn't hear you.
Do we know why the field is decreasing?
Yes, that is a very big question, and researchers in this field try to simulate the decrease of the magnetic field. And the Earth's magnetic field is created by the dynamo effect in the core or outer core of the Earth. So there is some interaction between the rotation of the Earth's core, it's a melted iron, and the magnetic field. But using the numerical simulation, they recently they are successful in creating of the geomagnetic field decrease. But it's a very complicated theory. So I'm not sure how to explain the magnetic field is decreasing. But using the numerical simulation, simulating the core motion and seed magnetic field, using that simulation, they are successful to decrease the magnetic field. And of course, we can predict how the magnetic field moment is going in future. It's decreasing or increasing, but actually we have no idea. We need a long-term observation. Do I answer to your question?
Yeah, thank you.
Okay, I think next was Kaylee.
Hi, thank you so much for your talk. I had a question. What are some challenges that you and your team have encountered when you're developing the dense network of geomagnetic field observatories in Japan?
Yes, one is maybe the find the location of install location, because as you know, Japan have a dense net, also this a dense network of the railways, and railway using the electric current to drive the train cars, and that electric current will much disturbance in the geomagnetic field observations. So it is very difficult to find the location separated from the train railways or cities. So we need to find a location of the rural area, but there should be the power line. There should be the power line or internet also. So that is the one difficulty to find the location. And another one is maybe the grant. Unfortunately, I have no special grant to construct this dense network. I'm proposing, but sometimes I fail. So I'm using other grant that is related to the space physics, satellite data analysis or something like that. So I need a special grant dedicated to this constructing of the deployment of this dense network. So that is and more, another one is maybe the manpower. I have some students, but not so many, just 2 or 3. So I need students or technicians to help me in deployment of this network. That's it.
Okay, thank you.
Looks like Tom is the next question.
Yeah, thank you again for the talk as well. Is there a particular advantage to placing these stations like at different latitudes along this longitudinal line? Would there be similar usefulness in putting them at the same latitude?
Yes, probably yes, I think. But in case of you have an interest in the distribution of the mass density in the space, latitudinal network is more useful because different latitudes corresponding to the different geomagnetic field line. If you have that point here, you can have the information of the mass density along this magnetic field line. So you can have information in radial direction in the space. But if you have a longitudinal direction, there's another advantage, I believe. So even in the station is located in different local time, you can have a global information from the geomagnetic from the geomagnetic field data. But in case of me, I'm living in Japan, and Japan have a not so big country and have easier to deploy in the latitudinal direction, not longitudinal direction. But in case of the US, you have a wide area continent in the longitudinal direction. So it is easier for you to deploy the longitudinal direction.
Got it. Thank you.
I have a question. How do you collect your data from your magnetometers that you have in this dense network?
Could you say that? Sorry.
Yeah, how do you collect all your data from this dense network?
Okay. Some station, for example, the Kakioka or Kanozan or Kawatabi, we have an internet, so we can collect mostly real-time data. But some other station, Haramachi, this is no network. So we ask people to go there in person and copy to the USB sticks and going back. But for the next week, I will go to the Shirakami and the Mutsu. And Shirakami have a network, internet. And Mutsu also have a network, but maybe using the how can I say, it's a mobile phone network, mobile router. So it may not be stable than the dedicated network, I believe. But mostly I want to collect the data through the network, but some station, it is not possible.
Oh, okay, I see. Thank you. Kyle has a question.
Hello. I was wondering if you have any plans on doing any electric field measurements as well, to maybe do some magnetotelluric measurement analysis.
Okay. Yes. Magnetotelluric. I have only small experience in the measurement of the electric current for magnetotelluric. So at present, I have no plan to make electric current, ground electric measurement in this dense network. Maybe it may be very special instrument is needed, I believe. So at present, I have no plan.
Cool, thank you. I heard there's some scientists in Germany that are trying to do that, and I was wondering.
Oh, okay. That's right.
They're interested in doing something similar. But thank you very much.
If you have interest in the GIC, in the ground inductive current, we need electric current measurement. But at present, I have no much effort, no much grant to provide to afford that instrument.
I have another question. Do you
Yes.
think that the magnetoimpedance sensors, the cheap ones, do you think they could completely replace the fluxgate magnetometers?
Yes. I mentioned this is cheaper than the fluxgate magnetometer, but the disadvantage of this sensor is temperature drift is much larger than fluxgate magnetometer. So I mean that when the temperature is changed, the output is also changed. So we need to keep the temperature of the sensor as much as possible to measure approximately. So in comparison with the fluxgate magnetometer, the temperature drift is about 10 times, one order larger than the fluxgate magnetometer. So in more detail, it's about 10 nanotesla or 20 nanotesla per degree. So when the temperature changed 1 degree, the output of the magnetic field is changed by 10 or 20 nanotesla. So it is very big than the fluxgate magnetometer. So in future, I'm not familiar with this electronics of this sensor. I'm working with a corporation of this sensor. So I'm making a request to make a low temperature drift for this sensor. That's the future improvement.
Okay, I see. Thank you.
But if we have only interest in such a short time magnetic field variation, that is 1 hour, this pulsation have a period, it's about 1 minute or 2 minutes. So during the 1 or 2 minutes, temperature may not change so much. So in that purpose, this sensor may be useful. But if you want to see the SQ variation, daily variation or monthly variation, temperature effect have a problem for the MI sensor.
Do you have in your magnetometer observatories around Japan, is there a way to keep the temperature stable around these small magnetometers?
Yes, for example, the Kakioka or Kanozan, these are maintained by the Japanese governmental agency. So this is a manned observatory. So some people, some operator are always working in this observatory. So these are the very well-suited observatory as they keep the temperature control. But in other place, just place on the field, so temperature is changing. And in case of mine, Kawatabi or Shirakami or Mutsu, I don't do any temperature control. But one possibility is to dig the hole on the ground and place the magnetometer. So because the temperature is a little bit stable than the out in the air, so that is the one thing to control the temperature, but not so much, right? Not so much effective.
Okay, I see. Thank you. Are there any other questions? Okay, if not, thank you everyone for coming, and thank you so much, Professor Nosé, for your talk. We
Thank you
all
for
really
listening.
enjoyed it. With that, thank you all for coming.
Thank you.
All. Thank you for joining, and thank you so much, Nosé-san. So yeah, let's keep in touch, and I look forward to future
course.
collaboration with you on your new concept of ground-based magnetometer. That is really fantastic.
Yes, of course. Yes, talk to you in future, near
Yes.
future, I believe.
Yeah, thank you so
Thank
much.
you. Thank you. Bye-bye.
Bye.